Minasan, konnichiwa, Zamurai Engineer desu. So in this video, let us take our discussion on next module number 10 about acceptable level of safety. Let's proceed. So acceptable level of safety, let's start with our course objective. PSD provides fundamental concepts, principles, and theories under structural analysis and design of steel elements in a structure. We have the list of the topics to be covered. We are on the major topic number 2. Under this, we are now on the last module of this major topic number 2. About acceptable level of safety. So, what do you mean? What we need to understand? So, the margin established between resistance and load, okay, in real cases, is intended to reduce the probability of failure, depending on the consequences of failure or unserviceability. Okay, so let's go further. So that's the main idea. The goal of this is actually to reduce the probability of failure. And how to achieve this goal when there is usually is insufficient information, not only information insufficient, insufficient knowledge about, insufficient scientific. So there are tons and tons of studies about steel, but we cannot say that our current knowledge is complete. For example, information available for a completely mathematical description of either load or resistance is not yet available. Okay, so but we want those to be studied, researched, and applied. So LRFD is one approach to solve this, and ASD is another. So meaning to say, even up to now, we cannot solve this type of design problem by rigid or pure scientific means. So that it is still scientific, but what we mean is not closely mathematical analysis and description. Okay, so we have what empirical formula, we have scientific observation rather than mathematical formulation and description. However, LRFD and ASD both have as their goal to obtain a numerical margin between resistance and load that will result in an acceptably small probability of unacceptable structural response. So what are the example of unacceptable structural response? Failure due to buckling, failure due to what? To deflection. So those are unacceptable, okay, structural responses. So there are about 10 being specified in the code and in our reference book. So those are some of the unacceptable structural response that we would like to design to study against to analyze our system and structural components in such a way that our suggestion would become relevant performance-wise, safety-wise, okay? Because the view of the discipline would be acceptable. The level of risk is now acceptable, even though there is no closed mathematical solution. Okay? So by just using numerical methods, okay, to allow our suggestion, bringing in an acceptably small probability of unacceptable structural response. So major differences between LRFD and ASD. Number one difference is of course, the method used for calculating the design loads. So there are 7 combination of load equation for LRFD and 8 load combination equation for ASD. And number 2 difference is the use of resistance factors. So in LRFD we use the phi, and in ASD we use the safety factor omega. So these two are the main difference. So again, LRFD using resistance factor, ASD using safety factors. Okay. So structural safety. We have a basic equation for design to be able to conceptually formulate and numerically calculate the values. So we must have the required strength that must be less than or equal to the available strength of the element. Okay, so the required strength meaning they are determined through an analysis, also called load effect. So they come from the loading. So they assume load. So what is the total amount of load that we can think of? Then we can compute the required strength. So it is on that side of the aspect on the load side. Okay. What about the available strength? It is determined through specification. So specification meaning these are properties, characteristics. So those properties and characteristics are already tabulated. That's why it could be specified as of now. Okay. And they are based on limit states and also called resistance. So the resistance of the material. So it means the characteristic of the material, the size of the material, the dimension of the material. Okay? So those are the things that are involved in related with an effect, okay, to the resistance of the element. So in general, if we are talking of load effect and resistance, so load effect is coming from the load, resistance is the capacity of the material. So the load effect, the load must be less than or equal to the capacity of the material or the resistance. Okay. So in mathematics, so the summation of gamma I times Qi. Okay. Qi is the load, so the different types of loads. Gamma I have the corresponding load factors. Okay. And we have to sum up all of them together from I is equal to 1 to the nth I, and that summation should be equal or less than the nominal, okay, from the nominal strength times or multiplied by the resistance factor. Sorry about that. So therefore, nominal times resistance factor is actually what we call resistance of the material. So while on the left side of the equation is what we call the required strength. That is the requirement due to the load. Okay, and the right side is the available strength. Okay, so going further, what are the design basis? Important definition. For example, let us use required strength RR for ASD. We are using RA. So required strength for ASD and RU for required strength LRFD. So any R is the required strength. It could be what? Concentrated load, it could be uniform load, it could be torsion, it could be flexural. Okay, so those are the possible representation for the R. Okay, what is our required? It is tension, it is compression. Next, nominal strength. So Rn. Okay, so nominal strength, it is a theoretical strength that we need so that we can multiply the phi, okay, to be able to get the available strength. So what is available strength? So RC is allowable strength. Okay, so available strength is the allowable strength. Okay, that is also equal to what? Nominal strength divided by omega, because omega is a safety factor and that is supposed to be greater than 1. Okay, and next is for available strength we have design strength, that is corresponding to the allowable strength. So the design strength is phi times nominal strength. So either allowable strength or design strength, okay, must be compared with the required strength. Okay, so therefore we can now think that Ru must be equal to or less than phi Rn. Okay, so design strength is for LRD. Allowable strength is therefore Ra is equal to or less than Rn over omega. Something like that. So therefore, doing it, writing it down to be our design basis for LRFD. Design shall be performed in accordance with this mathematical formula. So, just like what I've said, RU is equal to or less than pi Rn. So, RU is required strength. So, Rn, nominal strength. Pi is resistance factor. Okay. And pi Rn is equal to design strength. Okay. Or resistance factor or times nominal strength. So, resistance factor times nominal strength, that is design strength. What about for ASD? ASD, just like what I've said, RA is equal to less than Rn over omega, wherein RA is required strength, and omega is safety factor specified in chapters D through K. So, nominal strength divided by omega is what we call allowable strength. Okay. So, continue with the design basis for both LRFD and ASD. If we have what? Concentrated load, Pn is equal to Fy multiplied by Ag. So, Fy is the yield strength. So, and yield strength of the material, and Ag is the gross area of the material. So, multiplying those, we have what? The nominal load. So, pi for tensile. So, when we are talking about tensile strength, we will use the yield. So, pi is specifically equal to 0.9. Talking about tensile. Tensile again is 0.9. What about the safety factor? 1.67 is equal to omega. That is for tensile alone. So, we can use this because we have the LRFD. So, if we are talking of concentrated load, PU, it must be equal to or less than pi tension times P nominal. So, for ASD, we have this equation. So, we are using PA, meaning the required strength in ASD. And here, we have basic design values specific to our different load, different types of forces. So, either it is tension, flexure, shear, compression, and so on, or torsion. So here, there are 4 listed here. Tension, bending is flexural, shear, and compression. So there are tension and compression. They are usually called axial. So axial forces. So bending is called flexural. So axial and flexural, and then shear is also called shear. Okay. So with that, we can see that there are columns for ASD and LRFD, and the remarks, explanation, information corresponding to them. Okay, so for example, here if we are going to use these basic design values, this reference is based upon simplifying assumptions and arbitrarily selected limitations. Direct use of 2016 AIC specification may be less constrained and less conservative. So we have W, S, C, and MC shapes. So for W shape, STM A992, meaning Fy is equal to 50 KSI, Fu is equal to 65 KSI. So for S shape, C channel, and MC shape, we have ASTM 836, meaning FY is 36, FU 58. So for condition of tension forces, so we have AST 0.6 FY AG is equal to or less than 0.5 FU AE. So AE is the effective area, while AG is again gross area. So 0.5 is the factor, FU is the what? Ultimate, FY is the tensile. So we have what? For LRFD, the corresponding formula is 0.9, that is the load factor, 0.9 times FY AG must be equal to or less than 0.75 FU AE. Okay, so that is for tension. Okay, so you can compare it when we are going to use compression. Okay, for compression, ASD 0.6 FYAG, okay, and multiply by quantity 0.658 to the exponent P. Okay, so while in LRFD we have 0.9 FYAG times quantity 0.658 exponent P. Okay, so that is for what? For length to R ratio, LR ratio of between LC over R up to if LC over R is equal to or less than 800, divide by square root of FY. If LC over R is greater than 800, divide by square root of FY, we have another set of formula for AST, 150,000 times AG divided by LC over R quantity squared. Okay, while on LRFD we have 226,000 times AG divided by quantity LC over R squared. Okay, so what do we mean by P? P is equal to FY quantity LC over R squared over 286,000. So, and we have a note there, note 1.3. So let us go to note 1.3, not applicable to slender shapes. For slender shape, we have to use another value for AE from AIC specification in place of AG. So here we are just using AG. So for C channel and MC shape, CAC specification section E4. So these formulas are very specific. Okay, when we are computing the values. Okay, so for example, bending, we have another thing, and the the easiest here are computing the shear. For example, in ASD, 0.4 FY AV. Okay, so in LRFD, 0.6 FY AV, and C note 1.2. So 1.2 multiply equations given by 0.9 for W44 by 230, W40 by 149, W36 by 135, W33 by 118, W30 by 90, W24 by 55, W16 by 26, and W12 by 14, and all channel and MC shape. In weak axis, equation can be adapted by using AV is equal to 1.8 B with width of flange times thickness of flange. Okay, so width and thickness of flange, so that is AP. So what about for bending? There are formulas for strong axis or weak axis. Okay, so we'll give you the opportunity to take note of this formula. So what is important in this formula are the basic design value of according to different loading forms like tension, bending, shear. So there are different formulas for ASD and LRFD. Okay, so again, this is the last slide, a challenge question for material engineering examination. Question number 9. Shotcrete shall be applied within blank of adding cement to the mixture. So how much time is necessary that the shotcrete shall be applied? Okay, adding the cement to the mixture. So A, 30 minutes, B, 45 minutes, C, 60 minutes, D, 90 minutes. Okay. Again, Sam, this is Dr. EYPEI, teaching engineering for nation building. Thank you and see you on our next module.